Okay, so this is a comprehensive energy example that I came up with that involves all forms of energy that I can think of that we're going to be dealing with. So let's take a look at the situation and try to do a drawing of it. So we have a horizontal surface and a block. Okay, and this block is pushed back against a spring. So I'm going to have a place for the spring to be squished against, and then there's the spring. And this spring is characterized by something called K. So springs have two important aspects for us. One is that the force of a spring is K times the X of the spring. And a spring is a squishy kind of a device or stretchy. If you push on it, it exerts more and more and more force depending on how far you push it. And that's what this equation is describing. The more you squish the spring, the more force there is. And the other thing we care about with springs is the potential energy of a spring is 1/2 k x of the spring squared. And that's the equation we're going to be using to think about this spring. So what is this x of the spring? Well, this spring has a natural length. So this block is pushing back 7 centimeters, and I guess I could call it -7 centimeters. So if the block wasn't there, the spring would be stretched out all the way to the second dashed line. But because somebody is putting their hand on there and pushing the block back, the spring is compressed by 7 centimeters. So that's going to give this system some initial energy. Now this K value, that is this thing. That is the relationship between the force of the spring and the amount of stretch of the spring. So that's where that fits in. And we call it the spring constant. I think that's how they got the letter K, because the German word for constant starts with K. Hit mute all here. And that's one of the cool things about springs is even though the force is variable and depends on how much you compress the spring, that ratio between the compression and the force is always constant. Or most springs work in the other direction too. Instead of compression, this can represent extension or expansion of the spring. So the ratio between the force of the spring and the displacement of the end of the spring is always a constant. And of course, we have our m equals 0.25 kilograms because it is a 250-gram block. So we're going to care a little bit about kinetic energy. Ke is equal to 1/2 mv squared. Now let's see what happens next. So you push something about the spring and let go. That thing is going to spring. It's going to get pushed away. It's going to get launched. So what happens next? The surface itself is frictionless, but we're going to hit a skid pad. So I'm going to put a skid pad here. And I guess I forgot to say the length of the skid pad. Yeah, I'm going to make it. So it's going to be a 0.6 meter skid pad with a coefficient of friction of 0.4. So this is 0.6 meters. And that thing there has mu sub k, coefficient of friction of 0.4. So you can imagine what's going to happen to a sliding object when it hits a rough portion, a frictional portion. It's going to start slowing down. It's going to scrape against that surface and start slowing down. Now, after that, the friction coefficient goes back to 0, and the block slides up a 35-degree ramp. So after this, we're going to get to a ramp here where the angle of the ramp is 35 degrees. And eventually, the block's going to get to a maximum height, run out of steam, and the question is, how far up the ramp does it go before it comes back down? So we're going to have this diagonal distance, d is question mark. So apparently another form of energy that we care about here is the friction work. And the work due to friction is going to be the force of friction times delta x of friction. That's it's negative because friction is taking energy away, and we're going to have to calculate the force of friction, and then we're going to have to use that distance, the 0.6 meters, in order to figure out how much work friction does. And then the last form of energy we care about is gravity energy, which is the potential energy of gravity is equal to mgy. So we're going to have to figure out how to take that into account. So like I said, I created this example in order to have all possible forms of energy in our analysis. And generally, we want to think about the idea of initial plus work is equal to final. So we have to think about what kind of energy do we have, and that would be kinetic energy and potential energy. And there's two potential energies. There's spring potential energy, gravity potential energy. And then we want to think about how much energy we gain or lose. And the forms of energy we have are changed by the energy we gain or lose. So this energy we gain or lose is called work, and that's just the friction. So we're going to have kinetic energy initial plus potential energy of the spring initial plus potential energy due to gravity initial plus work due to friction, which we know is negative, equals kinetic energy final plus plus potential energy of the spring final plus potential energy due to gravity final. So I'm going to work right here on this screen before I scroll down, and let's calculate how much energy all these things are. Now, let's do the easy one first. When we say that the block is released from rest, that means that KE initial is equal to 0. So that's going to go in here as the first thing. So that's nice and easy. And when we say how far up the ramp does it get, that's telling me that KE final is equal to 0, because this thing is going to go up the ramp, and for a very brief instant, it'll stop and then come back down. And it's not going to be stopped for any extended period of time, just for an instant. So we don't have to worry about KE. Let's do the spring. EE spring initial is equal to 1/2 K X spring initial squared. So let's see here. Think, got it. So this is 1/2 times 220 times 0.07 quantity squared. And that, I believe, comes out to 0.539 joules. Let me check that calculation. 1/2. Yeah, I'm pretty sure that's right. Okay. Now, when we get to the end, there's no more spring. We're not in contact with the spring anymore. So EE spring final equals 0. So I don't have to worry about that. So far, so good. Work due to friction. Let's think about that for a second. We have to think about the force diagram. Force of gravity, force normal, and force of friction. And that's what allows us to say, oh yeah, this is one of those cases where the normal force is mg, and the force of friction is UK mg is 0.4 times 0.25 times 9.8. And our work due to friction is going to be negative 0.4, 0.25, 9.8, and multiply by distance 0.6. Because work is force times distance for a constant force. It works great. And if we calculate all that out, we get work due to friction. So 0.6 is my skid distance, 0.4 is that. So this is minus 0.4 times the mass times 9.8 times the distance. All right. Things wrong here. that's what went wrong. Okay. Okay, I did a mistake in my preliminary calculation, and I am going to fix it by changing this to 0.06 meters. So I'm gonna fix it by crossing it out. 0.06. Cross that out. 0.06. Because I set it up in a way that wouldn't work, so I don't want to do that. Okay, so now this is minus 0.0588. Okay. So you can see the minor correction I made in my given values here. Yeah, make that legible. Instead of a 0.6 meter, which would be 60 centimeters skid pad, it's now only a short 6 centimeter skid pad. All right. So now we've done enough numerical calculations in order to be able to get something useful out of our energy equation. So I'm going to go in here and fill in all the numbers that we know. We have 0 initial kinetic energy. And let me put in my symbols here with the regular pen. And we have 0 potential energy due to the spring. 0.539 joules. We have no potential energy due to gravity initially. We'll call the beginning y equals 0. And we have work due to friction of minus 0.0588. At the end, at the top, we have 0 kinetic energy. We have 0 spring energy. And the thing we're going to get out of this is potential energy gravitational final. So that's going to stay in the equation as a symbol. So now all I have to do is take my 0.539 minus 0.0588, which is 0.4802. That is going to be my potential energy due to gravity final value. So let me make sure I have my calculation set up over here. And we're just going to take that plus that negative number to get that. All right. So now what do we do with this? So let me summarize where we're at. We know the potential energy due to gravity. So this is mg final. We want to solve for y. So we'll take our 0.4802, it was joules, divided by mg, 0.25 times 9.8. So I'm going to take my amount of energy divided by parentheses mass times 9.8 and get 0.196 meters. So now we know how high it gets vertically. Now, let's do a drawing of this ramp because I lost that drawing. We have a ramp here, and our block is going to get up to here. And right now, we know this distance. So this is our 19.6 centimeters. And we know this angle, 35 degrees. And we want to know this distance here. How far up the ramp, like measured along the ramp, does this block get? So then we can do our trig. Sine theta is equal to opposite over hypotenuse. So hypotenuse is equal to opposite over sine theta. So that's D is equal to 19.6 centimeters over sine 35 degrees. So equals that over sine of that. So that's 34.2 centimeters. That was my final answer. So when this block is launched by the spring, it's going to have some fast velocity here. The skid pad's going to slow it down and take away this tiny little bit of energy. And then as it goes up the ramp, it's going to go slower and slower and slower till it gets to zero. And how far up the ramp does it go? We just calculated it 34.2 centimeters up the ramp. Now there are two other interesting calculations we can do. We can figure out how fast the block was going just after it was launched by the spring. So for that, we're going to look at a kinetic energy calculation, and it's Ke equals 1/2 mv squared. And we'll put in the kinetic energy of all of the spring's energy goes into the block. So that would be the 0.539 joules. So this will be 0.539 equals 1/2 times 0.25 times v squared, and then we get the 2 times 0.539 over 0.25 is equal to v. That would be v squared, but I don't want v squared, so I'll take a square root. This is very common algebra that we have to do, and I recommend practicing it until you get it right every time very quickly. So square root of 2 times 0.539 over 0.25 is v. And I'll round that down to 2.08 meters per second. Put that up there, right about there. Okay. So that's one interesting thing we can calculate. How fast was the block going at the base of the hill? So for this, we're going to do the same kind of calculation, but now our KE is equal to 0.539 minus 0.0588 equals 4802. Would be square root of 2 times 0.4802 over 0.25. Is only 1.96 meters per second. So just to review, initially, the spring had 0.539 joules of potential energy. That was given to the block as 0.539 joules of kinetic energy. The skid pad did some work, and we calculated that up here to be negative 0.0588 joules of work due to friction. And that left us with 0.4802 joules of kinetic energy. And that was converted into 0.4802 joules of gravitational potential energy by the ramp. So that is my big, long, comprehensive energy example where we thought about all of these different energy quantities along the way.